In the last videos, I talked about the derivatives of simple functions, and the goal was to have a clear picture or intuition to hold in your mind that actually explains where these formulas come from. But of course, most of the functions you deal with in modeling the world involve somehow mixing or combining or tweaking these simple functions in some other way. So our natural next step is to understand how you take derivatives of more complicated combinations. And again, I don't want these to be something to memorize. I want you to have a clear picture in mind for where each one comes from. Now, this really boils down into three basic ways to combine functions. You can add them together, you can multiply them, and you can throw one inside the other, known as composing them. Sure, you could say subtracting them, but really that's just multiplying the second by -1 and adding them together. And likewise, dividing functions doesn't really add anything, because that's the same as plugging one inside the function 1 over x, and then multiplying the two together. So really, most functions you come across just involve layering together these three different types of combinations, though there's not really a bound on how monstrous things can become. But as long as you know how derivatives play with just those three combination types, you'll always be able to just take it step by step and peel through the layers for any kind of monstrous expression. So the question is, if you know the derivative of two functions, what is the derivative of their sum, of their product, and of the function composition between them? The sum rule is easiest, if somewhat tongue-twisting to say out loud. The derivative of a sum of two functions is the sum of their derivatives. But it's worth warming up with this example by really thinking through what it means to take a derivative of a sum of two functions, since the derivative patterns for products and for function composition won't be so straightforward, and they're going to require this kind of deeper thinking. For example, let's think about this function f of x equals sine of x plus x squared. It's a function where, for every input, you add together the values of sine of x and x squared at that point. For example, let's say at x equals 0.5, the height of the sine graph is given by this vertical bar, and the height of the x squared parabola is given by this slightly smaller vertical bar. And their sum is the length you get by just stacking them together. Now, for the derivative, you want to ask what happens as you nudge that input slightly, maybe increasing it up to 0.5 plus dx. The difference in the value of f between those two places is what we call df. And when you picture it like this, I think you'll agree that the total change in the height is whatever the change to the sine graph is, what we might call d sine of x, plus whatever the change to x squared is, dx squared. So, rearranging, df divided by dx, the ratio of the tiny change to this sum function to the tiny change in x that caused it, is indeed cosine of x plus 2x, the sum of the derivatives of its parts. But like I said, things are a bit different for products, and let's think through why. And let's think through why in terms of tiny nudges again. In this case, I don't think graphs are our best bet for visualizing things. Pretty commonly in math, at a lot of levels of math really, if you're dealing with a product of two things, it helps to understand it as some kind of area. In this case, maybe you try to configure some mental setup of a box where the side lengths are sine of x and x squared. But what would that mean? Well, since these are functions, you might think of those sides as adjustable, dependent on the value of x, which maybe you think of as this number that you can just freely adjust up and down. So getting a feel for what this means, focus on that top side there, who changes as the function sine of x. As you change this value of x up from 0, it increases up to a length of 1 as sine of x moves up towards its peak. And after that, it starts to decrease as sine of x comes down from 1. And in the same way, that height there is always changing as x squared. So f of x, defined as the product of these two functions, is going to be the area of this box. And for the derivative, let's think about how a tiny change to x by dx influences that area. What is that resulting change in area df? Well, the nudge dx caused that width to change by some small d sine of x, and it caused that height to change by some dx squared. And this gives us three little snippets of new area. A thin rectangle on the bottom, whose area is its width, sine of x, times its thin height, dx squared. And there's this thin rectangle on the right, whose area is its height, x squared, times its thin little width, d sine of x. And there's also this little bit in the corner, but we can ignore that. Its area is ultimately going to be proportional to dx squared, and as we've seen before, that becomes negligible as dx goes to 0. I mean, this whole setup is very similar to what I showed last video with the x squared diagram. And just like then, keep in mind that I'm using somewhat beefy changes here to draw things, just so that we can actually see them. But in principle, dx is something very, very small, and that means that dx squared and d sine of x are also very, very small. So, applying what we know about the derivative of sine and of x squared, that tiny change, dx squared, is going to be about 2x times dx. And that tiny change d sine of x, well, that's going to be about cosine of x times dx. As usual, we divide out by that dx to see that the ratio we want, df divided by dx, is sine of x times the derivative of x squared, plus x squared times the derivative of sine. And nothing we've done here is specific to sine or to x squared. This same line of reasoning would work for any two functions, g and h. By the way, I should mention that if you multiply by a constant, say 2 times sine of x, things end up a lot simpler. The derivative is just the same as the constant multiplied by the derivative of the function. In this case, 2 times cosine of x. I'll leave it to you to pause and ponder and just kind of verify that that makes sense.